So in the previous mini lecture, we looked at the ANOVA formulation of the simple t-test, and the lecture before that, we looked at the ANOVA formulation of the linear regression. So this seems like a lot of work for mathematical expressions of statistical tests that we already knew how to run and that we can get identical results for. But now we start to extend the ANOVA framework. Right? We take advantage of its flexibility to start to do things that we couldn't do with simple t-tests or simple linear regressions. And so the first of these is to extend the ANOVA to multiple levels. So before we had category A and category B, mice on drug A, mice on drug B, but we can extend the ANOVA test to any number of levels within each category. And so here's made up data, say weight, for three genotypes, right? So you have a dominant phenotype, a double A, or a double A of one allele, right? So big A is one allele, little a is another allele, right? So you have a homozygote for one allele, homozygote for the other allele, or heterozygote, right? So there are three categories here, and we have made up data for weight, right? And again, the beautiful part of the ANOVA is that really as the data changes, our model doesn't necessarily change. What we type into R doesn't change. So I just have my data. I make my data into one factor called my data. I have my genotypes, that's the factor. And then I just put this into R and I say ANOVA my linear model, and out will come the results, right? And so the full model has this residuals, right? I mean, this starts to be pretty familiar. And again, the framework is nice because even as you change the underlying structure of the data, the basic steps you do to perform the ANOVA don't change, right? So I have a full model, and the full model has residual my linear model squared, right? So here's the sum squared of the error for the full model. The background model is still a one parameter model. So the residual there are just xi minus x average squared, right? And then I just grind through my formula, right? So there's my formula of residuals minus full divided by the degrees of freedom, divided by the full error residuals divided by the degrees of freedom of the full model. This is F distributed, so this is the number that I calculate, and this is F distributed with 2 as the first parameter, because there's this is a 3-parameter model, this is a 1-parameter model, so the difference in degrees of freedom is 2, and then the full model had 21 data points minus 3 degrees of freedom, so that gives us minus 3 parameters, and so that gives us 18 degrees of freedom for the bottom here. So I can do all of this and type all of this into my formula, or with much less typing, I can just say ANOVA my linear model, and all these numbers work out, right? So here's the same F value here. Here's the same probability of that this null hypothesis, evaluating null hypothesis that genotype doesn't matter. We get the same p-value here, and then again the degrees of freedom are 2, representing the difference in degrees of freedom between the full and the reduced model, and 18 representing the degrees of freedom associated with the full model. Visually, we can think of this as which of these are the better models. Right? So I have a 3-parameter model in which each genotype has a mean, and I measure the error, the difference between the residual sum squared, where for each category the error is the distance between this data point and the mean line, and so I sum up all of these errors. So do I explain enough of the variance here to justify these 2 parameters relative to this parameter, relative to this model, where I have a single parameter and I'm measuring the distance between each data point and the mean line. Right? So I have 3 mean lines here. I measure the error as the distance between each data point and the mean line, or I have 1 mean line here, and I measure the distance between each data point and the mean line. And the ANOVA test has a null hypothesis that these 2 models explain the same amount of variance. Another way of expressing that null hypothesis is that really these means are all the same, right? So the null hypothesis is that this equals this, which is to say that you can explain this with a model with only 1 mean, as opposed to needing 3 means. So again, this p-value tests the null hypothesis that the means are all the same. It does not tell us which of these individual means are different. We'll talk about doing a post-hoc test on the ANOVA in a second. Right? When we look at how R codes this up, so if we look at this x-intercept x, if we set x equals true when we formulate the linear model, right, then I can look at the data, right, and so my 3 parameters are b0 times this background intercept, and now I have one dummy variable that has 1 if you're big A little a, and 1 dummy variable that has 1 if you're big double A, right? The background here is little a, right? And so the background is these are zeroing these out. The ANOVA test zeroes these 2 out with respect to the background. And so we get all this information when we type summary. This is going to be the mean of the background genotypes. This would be the mean of little a, and this is the difference between these represent differences in mean between these different genotypes in the background. And the null hypothesis is that we can zero both of these out, and we explain the same amount of variance as when these B1 and B2 parameters are present. Now, of course, it's arbitrary which we choose as background. Now, here, actually, you can get different answers, right? It matters, but unlike the simple case where there's only two and it doesn't matter what you say the background is, here it does matter what you say the background is. So you do really want to think about how you use this relevel to set the background because you're going to be performing inference against that background, and it can matter in this case where we have more than two levels which one you choose as the background. So you often want to think carefully about how you use the relevel command and what you want to set as the background. Now, instead of running an ANOVA, you can also ask R simply to do every possible t-test. Right, so there's three possible tests. If you have three categories, then there's 3 choose 2 or 3 choose 1 possible pairs. And as an alternative to the ANOVA, which only tells you whether the means are all equal, right? So the ANOVA test is only saying, are these three means really the same as this one mean? Right? Are the means all equal? That's what the ANOVA test does. An alternative test, or a test that you might run in addition, is to run every pairwise t-test. And you would also, in that case, want to correct for multiple hypothesis testing, because if you had 10 categories, you would have a lot of 10 choose 2, whatever that is, a large number of tests that you can run. So we can also run a statistical model in which we consider the allele to be the dose, right? So let's say that we encode the our alleles as the dose of the little a allele, right? So then the dose would be 0, 1, or 2, right? In this case, we can then use 0, 1, and 2, which are not factors but are numbers. And if we put that into R, then instead of having our full model be these 3 levels, right, we are now going to try and fit a linear regression model where we have dose 0, 1, and 2. Right? And the only difference here when we do this is that instead of encoding the genotypes as big A's and big A's and little A's, we actually encode them as numbers. Right? So in the category in the X data here, right? Instead of this being a vector where you have big A's and like big double A's, heterozygotes big A little a, and heterozygote and homozygotes little a. Instead of that, you have numbers. Right? So you say I'm going to code A as 0. Double big A is 0, big A little a is 1, and double little a is 2, right? And then when I say my data squiggle genotypes, these are no longer factors. It's just a simple linear regression, right? So instead of trying to fit, it's the same data here, but instead of trying to fit a mean to each data point, R tries to fit a regression line. So instead of the full model having 3 degrees of freedom, the full model has only, instead of losing 3 degrees of freedom because you have 3 parameters, in the full model. So instead of having a full model with 3 parameters, you go to a full model with 2 parameters and you try to fit this with a line, right? And so we gain 1 degree of freedom. Our data now looks like this. Instead of having columns of dummy variables relative to the background, our intercept, our B0 now represents the y-intercept, right? So where we cross the y line here. And our b-intercept is the slope, and this is just our data, unlike any other linear regression. Right? So biologically, this is really different, right? So in one case, we're asking R to fit a mean to each one of these genotypes and test a null hypothesis that these 3 genotypes are equal. In this case, we're asking R to fit with 1 fewer degree of freedom because this is a 3-parameter model. 1, 2, 3. This is a 2-parameter model having the slope and the intercept. And in this case, we're asking R to make a linear fit between the dose of the genotype and whatever your data represents here, right? And then we test a null hypothesis that the slope equals 0. So we've gained 1 degree of freedom as our model just has 2 parameters. Again, this shows you the expressiveness of the ANOVA form. Because the way that we solve this equation doesn't change, right? This is you still are minimizing the residual sum squared errors of models, testing a full model to a reduced model. It's just, and the reduced model is always just this model, right, is the one parameter model where you fit a mean to the data and then measure the distance line, the distance of the errors to the mean. And so the reduced model is always here. But if we tell R that our data are categories, right? If we tell them that if we say that our X data are categories, right? That these are 3 alleles, not numbers. Then R fits a 3-parameter model, 1, 2, and 3, and measures the error in the full model of each data point to the mean of each category. If we tell R instead that the data are numbers, 0, 1, and 2, R just does a linear regression with a slope and an intercept and performs inference against the idea that the slope equals 0. But in either case, we still use this equation to find the parameters that minimize the residual sum squared errors, and then we do inference comparing the full and the reduced model. So this simple example shows the flexibility of the ANOVA model and the power of the ANOVA model to capture our different ideas about how we might want to model our data to maximize our biological meaning and our biological interpretation.